Good afternoon. Increasing trend in high-performance computing is to open and share clusters. For instance, in France at TGCC site, we have the Curie cluster made by Bull that is open to all European scientists that are eligible to the PRAISE program. So, of course, if you mean open, well, you will have to protect against external attackers. But at the same time, if you say shared, it means some kind of confinement so that legitimate users won't access data that they're not supposed to. As SELinux provides mechanisms for supporting control, access, security policies, it's a building block to implement cluster-wide protection. As a consequence, it will become mandatory to be able to run Lustre on compute nodes, on Lustre clients, where SELinux is enforced. So first of all, we'll try what happens if we just enable SELinux on a compute node and try to mount and run Lustre. Then if we are successful or obstinate, we'll see if we can manage to enforce security policies on Lustre. And then, because we do HPC, we'll have to measure the impact of security over metadata performance. Just to mention that for the rest of this talk, I assume a smattering of SELinux from the audience. I do not have time to recall SELinux basics during this presentation. Okay, so what if we try to mount and run Lustre on a compute node where SELinux is enabled? Let's have a look at the Lustre operations manual. So it reads, before installing the Lustre software, make sure you disable security enhanced Linux on all Lustre 7 clients. Then it adds, the Lustre software does not support SELinux. And finally, the SELinux system extension must be disabled on all Lustre nodes. So that's pretty clear that we should not use SELinux. But since LU 506 that landed in Lustre 2.3, before that we had a specific Lustre function, LLD add, that was replaced by a call to the kernel function dadd. And the good thing is that this function will call security instantiate if necessary. One of the purposes of this kernel function is to it will generate data structures that are used by SELinux. So simply with this patch, Lustre won't crash anymore if you try to mount it on a node where SELinux is enabled. So this is good news. It means we can use Lustre just as before. But what if we want more than just running Lustre as before? Maybe we could try to enforce security policies. The first step, of course, is to create a file and see what security information it gets. Here we can see that file 1 has the default T security context. But if we look at the file representation inside the MDT, we can see no extended attributes with the security information. It means that the information is not stored permanently, and it will have to be reset again on that file. So the first thing to do is to find a way to store the security information permanently. To do so, we made a Lustre code modification proposal in LU 5560. first thing is to when you create a file or directory, you call security inode init security. This function will properly initialize the security context of the file or directory you just created. It will put this information inside the struct inode representing the file or directory. And once we have this information, we will be able to set it in an extended attribute in the security.SELinux extended attribute, thanks to a call to llsetxettr. So with the patch, now we can see that we get a proper security context, file T. And if we look inside the MDT, we can see that we do have the security.SELinux extended attribute containing the security information. So this is good. Now that we have stored in security information permanently, we can try playing with security policies. So if we have an unconfined SELinux user, as expected, this user can do anything, and you just continue to access to all your files and directories in Lustre as before. So this is expected. Now, if you have a specific SELinux user, well, again, this is expected by default. All accesses will be denied, and you will have to write a specific security policy so that you decide what kind of actions you allow for this user on file and directories of that security context. So I have put a little extract of a security policy, giving all the operations allowed for user T on files and directories of context file T. Here we could imagine to have a specific Lustre security context, like for instance Lustre T, so that if we write a security policy, we make sure that it only has effect on Lustre files and not files that have the same security information. Another test case now. Because Lustre is a distributed file system, we can try to see what happens if we modify the security information from another node. So on node B, we use the chcon command as an administrator to modify the security information. Here we put home T. We can see that this information is propagated to the MDT, and it is stored in the extended attribute security.SELinux. So this is good. But the bad news is that on node A, we still see the former security information because we still have the file T security context. So it means that we will have to do something more inside Lustre to deal with security information coherency. This is a very special case. The normal SELinux workflow is to set security information at file creation time, and then you never modify it. Only administrators under certain circumstances want to modify this information, but this is not a common workflow. Anyway, because we have a distributed file system, we still need to address this scenario. As I said earlier, the security information is primarily set inside the struct inode. And the extended attribute that contains the security information is only used at lookup time when you first access the file or directory. So the idea is to ensure that the extended attribute is read for every file access, So we try to drop inodes after every use. So this is why we define the drop inode function to be generic delete inode. And with this, after every file or directory use, the inode will be dropped from cache. We made this proposal inside LU 5560, and we're still discussing with Intel. You will see why. Okay, so we all do HPC, so we have very demanding users, and they want features, but at nearly no cost, if possible. But we all know that it's not the case, but we have to measure this impact. So the test system I used is very simple. It is made of one client node and one server that combines MDS and OSS functions, and it uses ramdisk storage. We use the MD test metadata benchmark in directory per process mode. So it is when every process writes and reads files in a dedicated directory. First of all, we tested the code where we store the security information inside the security.SELinux extended attribute. So this is Lustre 2.5.2 plus this code setting the extended attribute. The first objective is to see the impact of our metadata performance. And the second objective is to see if we can benefit from the extended attribute caching mechanism that was developed inside Lustre. First test case is file create. So the blue line shows the performance we get with SELinux, without SELinux, sorry. The red line is with SELinux enforced. The performance is lower by around 35%. And this is because at creation time, we have to set the security.SELinux extended attribute. So it requires more work and more communications between the client and the MDS. We can see that the performance is even slower with the extended attribute cache enabled. And this is because this feature is a read-only cache. It means that it is filled at read time, but it is cleared at write. So because we do a set xattr operation, the feature has to try to purge the cache for the corresponding entry. So this requires even more work. Second test case is with filestat. So we have cleared the cache between file creation and filestat, so that the system cache does not contain any inode. Here again, the performance with SELinux enabled is slower by 35%, because this time we have to do a get xattr operation, which requires communication between client and MDS. And the performance is even slower with the extended attribute caching enabled. Here, because we have to fill the cache with the security information and put it in the entry corresponding to the security.SELinux extended attribute. And also because this feature requires to enqueue an additional log. So it multiplies the communication between the client and the MDS server. Now restart. So this time we keep the system cache with all inodes in it. And that time we can see that all performances are pretty similar. And this is because I explained earlier, the primary location of the security information is the struct inode. So as long as this information is in the system cache, it is stored in the slab, the performance is not impacted if you have just to look for one more thing in the slab. Last test case is file remove. With few threads, with SELinux, we suffer from the additional get xattr operations. And we can see that starting from 4 threads, the MDS becomes the limiting factor, and this is why we reach the maximum performance. Again, with extended attribute enabled, the performance is slower because in that case we will have to fill the cache with the when the getExecTTR operation occurs before removing the file. So this is a completely useless operation occurring here. The test summary is, of course, you may have understood that extended attribute caching does harm to metadata performance when we have SELinux enabled. So we could imagine to modify the extended attribute cache mechanism so that it does not try to cache the security information, just like it does at the moment with ACLs. The second conclusion of those tests is that, in the end, the performance at maximum is lower by 1/3. So this is pretty good news. We know that we have a limited impact of SELinux over metadata performance. Now, other performance tests with the feature to ensure security information coherency. Again, this is the same code plus the code that drops inodes after every use. So let's see if it is a viable solution. The answer is no. Of course, with this code modification, Lustre becomes a file system with no cache, and so it suffers from that a lot. Performance is really terrible. So probably a best solution could be to rely on a LDLM lock, so that we drop inodes only when it's necessary and when a competing client wants to have access to the security information. And this is the end of my talk. To sum up, we have seen that it's now possible to mount and run Lustre on nodes where SELinux is enforced. Thanks to the patch we proposed in LU 5560, we are now also able to enforce security policies on Lustre nodes, and with a limited impact on metadata performance of about 1/3. Of course, we still have to address the coherency scenario. Again, it is not the standard SELinux workflow, but anyway. And of course, we will rerun performance tests to measure the impact of this new solution. Thank you. Do you have any questions?
Would it be possible to have the server do the actual set executr at creation time? Because if you share the rules, then it can find out what it's supposed to put in the inode and do the set executr itself.
I'm sorry, could you repeat? I cannot hear you.
If you share the rules between the server, MDS, and the client, you could have the server do the set executr itself without an extra RPC. Would it be possible to do something like that?
You mean to have the set executr done in the same RPC as the
yeah, basically the
MDS
decided what it's supposed to put based on the same rules. So
I don't know. I don't know Lustre mechanisms at that point, so I don't know if it's possible. It would require a protocol change, I think. So it might be hard to implement.
I think just turning SELinux on the server should do it automatically without anything else.
Is there any performance drop if you're using SELinux only on clients? So as I understand your graphs, what you showed, right? So it was when you have your servers with patches.
No.
But
No. We only focused on SELinux on clients. So all performance I presented here are valid if you have SELinux enabled on the compute nodes only.
Okay, thanks.